Very good morning, everyone. Today, my TikTok topic is about on complex conjugate pair sums and complex conjugate subspaces. I am G Naresh from ECA section. This PPT is about the subject CASF. Initially, we consider an LTI system whose impulse response is one period data of complex conjugate pair sums for an given input x of n. We prove that output of the system is equivalent to computing the first order derivative of x of n. For a given q belongs to n, define a set complex exponential sequence of h suffix q is equals to sq comma kn is equals to e power j 2 pi kn by q, where q is less than equals to k less than equals to q minus 1, and it denotes the greatest common divisor GCD, which is shortened known as GCD, between the k and q. By adding all these elements of HQ, mathematician Srinivasa Ramanujam introduced the trigonometric summation called as Ramanujam sum, which is shortened known as RS, and it is denoted as CQ of n. So, by this trigonometric summation, this complex conjugate pair sum is introduced as k comma q is equals to q minus k comma q for every s of q k of n belongs to HQ. There exists a complex conjugate sequence SQQ minus k of n belongs to HQ, both together for the complex conjugate pair. Complex conjugate pair sum is denoted by adding each complex conjugate pair, that is CQ k of n is equals to 2m cos of 2 pi kn by q. Here m is equals to 1 by 2 if q is equals to 1 or 2, or else m is equals to 1 if q is greater than equals to 3. If q is greater than 1 and k is equals to 1 if q is equals to 1, reinforce notations for u power q. We provided a new basis for CSS using CCPS. Further, a finite length signal is represented as linear combination of the signal which belongs to complex conjugate subspaces known as complex conjugate periodic transformations, which is known as CCPT. Contributions of this letter can be divided into two parts. So this contributions is divided into two parts. The first one is we show that the operation of linear convolution between a signal x of n and c bar q comma k of n is another signal is equivalent to computing the first derivative of x of n, where c bar q comma k of n denotes one periodic data of c q comma k of n. So c bar q k of n denotes one period data in which the major signal is c q comma k of n. This operation is also equivalent to the second derivative if we consider an odd number q and the circular shift of q minus 1 by 2 for c bar q comma k of n. Then the problem of edge detection in an image is addressing using these derivative equation operations. Moreover, we compare this result with the result obtained by the RSS, which is denoted by Srinivasa Ramanujam. So here RS is a Ramanujam sum. In this second part, we prove the following properties, like complex conjugate subspaces is a shift invariant subspace, and since complex conjugate pair transform is an non-orthogonal transform, we compute the projections of complex conjugate subspaces. Further, we show that the projection matrix is circulant matrix, which reduces the computational complexity of projections. CCS is closed under circular cross correlation. Moreover, the circular autocorrelation of any finite length sequence is equals to the weighted linear combination of these properties of autocorrelation. So, the circular autocorrelation of a finite length sequence, which is equals to the linear combination of autocorrelation functions. In here, CCPS has derivatives and applications. Here, we perform an operation using CCPS, which is complex conjugate base sums, which is equivalent to the derivative. In particular, we prove the following theorems. So, in the first theorem, consider an LTI system, which is linear time invariant system, whose impulse response is C bar q, k of n, where q is greater than 1. Then, for a given input x of n and output y of n. Here we are giving the input as x of n and taking the output as y of n for a linear time invariant system. So, x of n into C bar q, k of n is equivalent to computing the first order derivative of x of n. So, when we coming to proof, let x of n is equals to c, where c is constant value. Then y of n is equals to c summation of l is equals to 0 q of n c bar q, k of l is equals to 0, has summation l is equals to 0 to q minus a c bar q, k of l is equals to 0 for q is greater than 1. If this is the equation 2, which implies output 1, which is y of n. If x of n is equals to u of n minus n naught, where u of n is a unit step sequence, then y of n is equals to summation l is equals to 0 q minus 1 c bar q, k of l into u of n minus n naught minus l, where u of n minus n naught is unit step sequence which starts from n and ends up to n naught. Here y of n is not equals to 0 and n naught is less than equals to n less than equals to n naught plus q minus 2. Then y of n is equals to n of summation l equals to 0 to q minus n c bar q, k of l minus summation l equals to 0 q minus 1 l c bar q, k of l. Here the first one is equivalent to 0 when we substitute the l is equals to 0 to q minus 1, and the second one let we say as p. So from the p term we can write it as summation l is minus m into summation l is equals to 0 to q minus 1 l into e power j 2 pi k l by q plus summation l is equals to 0 to q minus 1 l e j power 2 pi k l by q, where this e power j by 2 1 is came from the equation here kn is equals to e power j by 2 pi kn by pi. Here it is. From this it has came out. So So this is equivalent to MQ. Click to add from the above analysis, that is the system output is 0 for constant input, non-zero at the on transient of the unit step sequence, and the third one is also non-zero constant along the ramps. In the constant of image processing, any function or operation satisfying the above three properties is equivalent to the first order derivative. Therefore, x of n into c bar q comma k of n is equivalent to the computing the first order derivative of x of n. Further, with some modifications in the impulse response, the above operation is equivalent to the second order derivative. So the first order equation is therefore x of n of equivalent to computing the first order of x of n. So by multiplying x of n into c bar q of k of n, this first order equals to the second order derivative. To be a second order derivative, the system output should satisfy the first two conclusions, and it should be 0 for x of n is equals to n. That is, the term p should be equals to 0. But the assumptions of c bar q comma k of n has impulse response leads to p is equals to mq. So that is the term p should be equals to 0. Here it is the term of p, it should be equals to 0, but we are getting it has mq. So instead of c bar q comma k of n, we try by considering its circular shifts as an impulse responses. So we have considered it, we should consider it in the circular shifts as an impulse responses, so that we get summation L is equals to 0 to q minus 1 L into c bar q k L minus m is equals to q by 1 minus cos v into cos u plus v minus cos u, where 1 is less than equals to m less than equals to q minus 1, where u is equals to 2 pi km by q and v is equals to 2 pi k by q. So cos u plus v is equals to cos u. Here the figure 1 depicts cos u plus v versus cos u for the different q and k values. It is observed that independent of k, both the values are equal whenever q is odd number and q is equals to m is equals to q minus 1 by 2. Hence we can summarize the above discussion as these diagrams. So here the black line indicates cos u plus v is equals to cos of 2 pi km plus 1 by q, and the red color lines impulse responses are the cos of u impulse responses, which is equals to cos of 2 pi km by q. In the figure 1, here in the figure A, q is equals to 7 and k is equals to 2, so that we get impulse responses as shown. And for the other figures also, the values of q and k are changing, so that we can get different types of impulse responses. Here in the figure we came to know that cos of u plus v versus cos of u for different image processing. By changing different values of q and k, we get different images as shown. Complex conjugate subspaces. Construct a circular matrix dqk belongs to mq of r as given below, so that dqk is is equals to C bar QK to C bar minus L QK, so on, C bar Q minus 1 QK, where C bar L QK indicates I times circular downshift of the sequence. C bar QK, using the factorization property of dqk, we can write dqk is equals to bq comma k into bq comma k power h, where bh of q comma k is equals to sqq minus k of 0 and sqq minus k of 1 and so on, sqq minus k of q minus 1, and it is a 2 by q matrix. The column space of dqk is equals to vqk. Let q1 belongs to n and q2 belongs to n, and where n is equals to LCM of q1 and q2. Then the orthogonality property of complex conjugate pair sum is C power L1 in transpose and C power L2 transpose L2, where C power L2 is n by 1 matrix equals to 2n m cos 2 pi k1 of L1 minus L2 by q1, and the impulse signal of q minus del, that is del of q1 minus q2 into del of k1 minus k2, where c qi comma ki power li is obtained by repeating cqi and ki power li periodically n by qi times. Using this, we can conclude the following: the vector is the basis of vqk and not orthogonal. The subspaces vq1, k1 and vq2, k2 are orthogonal to each other. So by that we can prove that the subspaces vq1, k1 and v suffix q2, k2 are orthogonal to each other. So from this we can conclude that we have shown how to use complex conjugate pair sum has first and second derivatives. Here the first order derivative is used to find the edges of an image shown different image processing by changing q and k values, and later we discussed few objects of complex conjugate subspaces which may find their applications in the signal processing. Thank you.